On the morning of November 29th, 2025, something subtle, almost invisible, appeared in the motion charts of 3I-ATLAS. At first, it was a margin of error discrepancy, a tiny deviation in trajectory logged by the solar dynamics team at the Arnaves Observatory. Nothing anyone would notice at a glance. But as fresh tracking data came in, the line between predicted and actual path began to shift. Gently, but consistently. This wasn't a random fluctuation, it was acceleration, and not the kind caused by gravity. The first to raise the flag wasn't a government agency, but a group of independent orbital analysts who had been quietly tracking ATLAS since its re-emergence after solar conjunction. Using time-stamped angular positions and Doppler shift measurements, they calculated something off. A non-gravitational component had crept into the equation. It wasn't massive, just a few millimeters per second squared, but it was persistent. And in orbital dynamics, persistence means intent. Something was pushing. Non-gravitational acceleration in comets isn't new. It's usually explained by outgassing, volatile materials like carbon dioxide or water ice sublimating under solar heat, creating jets that push the object like a microscopic thruster. But 3I-ATLAS wasn't supposed to be that active. Not now, not at this distance, not after perihelion, and certainly not without the telltale signs of massive outgassing, a growing tail, a brightening coma, or sudden fragmentation. Instead, it remained strangely silent, symmetrical, intact. The community reaction was fast and split. NASA's JPL database updated its orbital elements, quietly accounting for the anomaly without fanfare. But in private forums, astrophysicists and orbital engineers began circulating overlays of trajectory models, watching how the object's path slowly began to bend, not dramatically but measurably, toward the orbital shell of Earth. It was no longer just moving through space, it was adjusting course. The timing made it more bizarre. This was weeks after perihelion, when most comets lose activity as they recede from the Sun. But this one had started speeding up, against predictions, against thermodynamic expectations, and strangely, against silence, because there was no matching rise in coma brightness, no debris arc, no radiation trail that would indicate what was causing the momentum shift. It was as if the object had found a new gear, but kept it quiet. The strongest confirmation came from a 3-frame comparison released by the IAC in Tenerife. By stacking high-resolution frames from November 27th through 29th, and compensating for Earth's motion, they produced a vector analysis showing that 3I-ATLAS had deviated from its projected arc by nearly 1.4 arc seconds. Far too much for observational error. That deviation, translated to distance, meant the object had gained speed. Not from a gravitational slingshot, not from a known body, but from somewhere. And this brings us to the first question scientists are still debating. What started the acceleration? Was it a delayed internal outburst masked by viewing angle, a subsurface volatile that erupted quietly? Or was the cause non-natural, a structural shift or internal mechanism we've never recorded in cometary behaviour before? No one knows. But on November 29th, the facts became undeniable. 3I-ATLAS had begun to accelerate, not randomly, but along a trajectory that now intersected more closely with Earth's orbital lane. And in astronomy, a trajectory change is never just math. It's a signal. The only question now was, of what? By late morning on November 29th, the orbital simulation dashboards at observatories across Europe and South America started flagging inconsistencies. It began with subtle alerts. Deviation thresholds exceeded, anomaly filters tripped, ephemeris curves out of sync. Most analysts assumed it was a data lag or a bad input from a regional observatory, but within 6 hours, it was clear this wasn't noise. The predictive orbital models for 3I-ATLAS were no longer in agreement. The divergence began in the simulations that relied heavily on photometric stability. Models assuming ATLAS was a passive, naturally drifting object obeying gravitational dynamics and solar radiation pressure. These are standard comet tracking equations. They work because most comets are simple: frozen nuclei, predictable outgassing, elliptical or hyperbolic escape arcs. But ATLAS had started to misbehave in ways no passive model could accommodate. Two distinct families of trajectories emerged. The first, grounded in old assumptions, showed ATLAS continuing its slow outbound drift past perihelion, coasting through the solar system on a hyperbolic exit path, untouched except by gravity. The second group, newer, far more reactive, began including non-gravitational components. These took into account unexplained radial velocity increases, like a hidden force pushing ATLAS off script. Suddenly the divergence widened. By midday UTC, the outbound trajectory predicted by older models had ATLAS 14,000 kilometers further along its path than the updated ones. That might seem minor on a cosmic scale, but in orbital mechanics, that kind of mismatch is enormous. It means that in just days or hours, two models that once agreed now place the object in completely different regions of space. The source of this shift was traced to the change in transverse acceleration, a sideways nudge that classical outgassing could not explain. If a comet vents gas as it nears the Sun, the resulting acceleration should be radial, pushing it away from the solar centre. But ATLAS wasn't just being pushed back, it was being steered, ever so slightly, sideways. That alone broke several simulation packages. NASA's JPL Horizon system posted an updated solution set that quietly incorporated a small non-gravitational parameter, labelled A2. The documentation didn't speculate on the cause, it just acknowledged the need for adjusted force coefficients to maintain trajectory accuracy. But what does A2 really mean? In comet dynamics, it's a variable assigned when the object's path defies pure gravity. Usually it means outgassing, but without a visible tail, coma expansion, or fragmentation. That left the field with two options. Something invisible was exerting force, or something internal was generating thrust. Astronomers began revisiting older cases of trajectory divergence, most notably Oumuamua, the first interstellar visitor ever observed. Back in 2017, it had also shown unexplainable, non-gravitational acceleration with no visible mass loss. The same pattern was now repeating, but with ATLAS the acceleration came after perihelion, during a phase where such behaviour should be declining. In Switzerland, the Geneva Observatory ran comparative simulations overnight, layering outputs from Horizons, ESA's Gaia corrections, and amateur photometry from Spain and Thailand. The conclusion was jarring. We are witnessing real-time orbital divergence caused by forces that are not modelled in current comet equations, one analyst wrote in a private Slack group, and it's accelerating. By the end of November 29th, the models were no longer converging. They were splitting, not slightly, but categorically. One group still treated 3I-ATLAS as a comet. The other cautiously began describing it as a variable mass, variable force object, language more common in aerospace engineering than astronomy. The models had diverged, and now every next observation wouldn't just track a comet, it would test a theory, or expose a mistake no one was ready to name. When objects in space accelerate, the direction of that force tells you everything. Comets, for instance, are pushed away from the Sun by solar radiation and outgassing. That's called radial acceleration. It aligns with our expectations. But on November 29th, 3I-ATLAS did something far more unusual. It began to shift sideways, experiencing what physicists call a transverse push, a change in motion that runs perpendicular to the line between the object and the Sun. And that one detail changed everything. In orbital dynamics, transverse acceleration is rare, especially in comets. For a naturally outgassing body, gas jets typically vent from the sunward-facing side, pushing the object directly outward. A sideways force implies either asymmetric outgassing, where jets fire at odd angles due to irregular surface geometry, or a completely different propulsion mechanism. At first, scientists assumed this push might be an illusion. Maybe it was a byproduct of Earth's viewing angle or parallax distortion from our orbital motion. But within hours, multiple ground-based observatories confirmed the data. 3I-ATLAS's orbital arc was subtly curving, not away from the Sun, but laterally across its predicted exit path. It was moving off-axis, bending its projected flight path in a direction no passive comet should go. This was the birth of the transverse anomaly. To isolate the shift, researchers began comparing angular velocities in right ascension and declination between November 25th and 29th. When plotted, the differences formed a parabolic deviation, evidence that the force wasn't random but sustained. The object had acquired a new velocity vector, and it was not radial. More troubling was the lack of visual cues. no outbursts, no coma expansion, no visible jets. If ATLAS was undergoing a symmetric outgassing, it was doing so silently, or in wavelengths we weren't observing. That led teams at NASA's Goddard Space Flight Center to cross-reference the trajectory changes with recent ultraviolet and infrared data from SOHO and Stereo A. The conclusion was baffling. While infrared imaging showed a modest increase in CO2 venting, the scale of the observed transverse motion required a much larger reaction force than any known outgassing could produce. That left theorists with a dilemma. Option 1. The object was venting from multiple jets hidden beneath a surface layer of regolith, and we just hadn't resolved them yet. Option 2. The force wasn't caused by outgassing at all. This is where the whispers began. Because if you eliminate natural causes, you're left with non-natural ones. Could the transverse push be the result of internal momentum redistribution? Could ATLAS be rotating, and something inside was shifting, mass moving within like a flywheel or counterweight? Or worse, could it be under autonomous control, reacting to the solar environment, making course corrections in a way designed to avoid detection? The concept was not unprecedented. In 2018, the same type of unexplained lateral motion in Oumuamua triggered similar questions. Avi Loeb, one of the few scientists willing to ask them out loud, resurfaced on November the 29th with a short post. Transverse acceleration without corresponding visual outgassing is not just a deviation, it is a data point. The rest is interpretation. And interpretation is where things become dangerous. Some speculated about electromagnetic interaction. Perhaps the object was reacting to the sun's magnetic field, riding its Parker spiral like a sail. Others proposed a more structured explanation. The force was self-induced, either by internal venting, controlled rotation, or a propulsion method beyond current comet models. Whatever the case, the push was real, and it wasn't random. By the evening of November 29th, 3I-ATLAS was no longer just a body being dragged through space by solar gravity. It had become a variable, accelerating object, changing its trajectory in a direction nature rarely allows. And nature, when challenged, always answers. The only question was how. By the evening of November 29th, the conversation around 3I-ATLAS had shifted from awe to skepticism. Not because it had stopped doing strange things, but because it was doing too much, with too little visual explanation. The comet had shown measurable non-gravitational acceleration, specifically a sideways transverse push, and yet there was no corresponding trail of evidence. In cometary science, outgassing is the standard explanation for these anomalies. When a comet nears the Sun, the heat causes surface volatiles, primarily water, carbon monoxide and carbon dioxide, to sublimate. This release acts like a natural thruster, creating jets of gas that push the nucleus in the opposite direction. That process leaves fingerprints everywhere: tails, bright comas, shock fronts, jets captured in time-lapse exposures. But with 3I-ATLAS, the data told one story, and the visuals told nothing. Across global observatories, from Chile to Norway, astronomers aligned their sensors, captured long exposure frames, stacked data, and enhanced contrast filters. They expected to see coma thickening, or at the very least dust ejection trails. Instead, what they found was a persistent silence. The nucleus remained clean, eerily symmetrical. The coma, faint and unchanging. There was no tail forming in the direction opposite the Sun, no fragmentation trails, no new debris cloud. The object that was now accelerating looked visually calm. This absence forced teams to revisit every angle. Were they missing something in the wrong light spectrum? Was the outgassing invisible to optical sensors? To answer that, they turned to infrared and ultraviolet data from JWST, SOHO, and Stereo A. JWST, which had previously detected an unusual dominance of carbon dioxide in ATLAS's spectral signature, was again triggered to observe. But while it detected a continued presence of CO2 molecules, the volume wasn't nearly enough to account for the scale of acceleration being observed. In fact, the rate of gas release was so low, it was consistent with a declining activity phase, not an active thrust. That mismatch grew more problematic when orbital modelers ran the momentum equation backwards. They calculated the amount of mass that would need to be expelled per second to achieve the observed acceleration. The answer was staggering: thousands of kilograms per hour, an amount that should have formed a vast debris cloud, easily visible even to amateur astronomers. But no such cloud existed. So where was the missing mass? Where was the evidence of that violent ejection? Some experts proposed that perhaps the jets were venting from the far side, hidden from our current viewing angle. Others theorized that subsurface venting was occurring, internal gas building up and escaping through porous regolith without creating visible plumes. But even these scenarios couldn't explain the symmetry of the coma. A jet strong enough to alter trajectory would still disturb the surrounding cloud, creating telltale streaks, distortions, or brightness, gradients. Atlas's coma remained stable and perfectly centered. This led to a radical proposition. What if the object was accelerating without any mass loss at all? This would place Atlas in the realm of non-natural propulsion, or at least non-conventional physics. Ideas began to circulate. Could electromagnetic forces from the sun be inducing motion through interaction with charged material on the object's surface? Was there an unknown internal mechanism, a venting process that leaves no detectable particles or gases behind? Could the force be mechanical, even artificial? The implications were uncomfortable, because in every past cometary case, acceleration without visible outgassing never lasted. The mystery always gave way to a missed jet, a late-discovered outburst, or an image with better resolution. But Atlas was different. The mystery wasn't fading. The harder scientists looked for outgassing, the more it seemed like there was none to find. In the language of celestial mechanics, every movement has a direction, and every direction has meaning. When a comet accelerates, we ask where it's being pushed. For most comets, that push comes from radial acceleration, a natural consequence of solar heating. As volatiles sublimate, gas vents outward, pushing the nucleus away from the sun, like a slow-motion rocket recoil. This is expected, measurable, and entirely within the laws of physics. But on November 29, 2025, something far stranger happened. 3I-ATLAS began exhibiting not only a faint radial acceleration, which would be normal, but a growing tangential shift. This is motion not directed outward from the sun, but rather across its orbital path, sideways, curving, slipping around like a wheel losing traction. In the precise world of trajectory modelling, where numbers are sacred and margins are microscopic, this is a red flag. The distinction is critical. Radial acceleration can be explained by solar activity and heating. It's a well-documented process seen in thousands of comets. But tangential acceleration implies a redirection of motion, not just a boost in speed. Something was not just pushing Atlas harder, it was pushing it in the wrong direction. The first signs came from differential position measurements logged across 3 observatories: Mount John in New Zealand, Kitt Peak in Arizona, and La Palma in the Canary Islands. By comparing the object's position against background stars over time, analysts detected a lateral deviation. Atlas wasn't just speeding up, it was sliding. The implications of this shift are profound. In orbital dynamics, any deviation that isn't radial must be caused by non-uniform mass loss, anomalous momentum, or external force interaction. But Atlas had no visible jetting, no ejection plume, and no electromagnetic interference that could account for the redirection. That led to renewed scrutiny of the vector breakdown. Radial acceleration. R. Movement directly away from the sun. Tangential acceleration. At. Movement along or against the path of orbital motion. Normal acceleration. An. Motion perpendicular to the orbital plane. In a standard comet model, R dominates. The comet outgasses, and the radial vector stretches. At and an remain minimal unless the comet is highly irregular or spinning rapidly. But with 3I-ATLAS, data showed a growing at component, a subtle but undeniable pull that curved its trajectory away from its previous hyperbolic path and closer to Earth's orbital shell. How could this be happening? One idea involved asymmetric jetting from beneath the surface. If a subsurface vent opened off-center, angled relative to the axis of motion, it could cause lateral thrust. But again, there was no observable activity on the visible hemisphere. Infrared scans didn't detect localized heating. UV readings didn't show directional plumes. The coma was smooth, unchanging. Another hypothesis involved rotational modulation, that perhaps Atlas was spinning in such a way that periodic venting created pulsed directional thrust. but for that to happen, you'd expect visible coma wobble, asymmetric dust trails, or outburst flickering. Yet ATLAS remained visually serene. This left the uncomfortable option. The tangential force was intentional, or at least regulated by unknown internal physics. Whether through engineered design, or a form of subsurface behaviour we've never seen, ATLAS was altering its trajectory in a calculated way. Not erratically, not chaotically, but with smooth, sustained precision. By the end of November 29th, observers updated their plots. The hyperbolic escape path, once thought to guarantee that ATLAS would slip back into interstellar space, had shifted, slightly, imperceptibly to most, but enough to bring it closer. Not to Earth itself, but to Earth's orbital domain. A radial push is natural. A tangential drift, that's something else entirely. When ground-based observations began to show troubling anomalies in 3I-ATLAS's motion, the first instinct was to verify those findings using a broader vantage point. Enter NASA's MAVEN spacecraft and the Solar and Heliospheric Observatory, SOHO. Two instruments designed not to monitor comets, but to understand space weather, solar activity, and atmospheric interactions. Still, both have a history of picking up more than they were built for, and in late November 2025, they quietly began recording data that confirmed what telescopes on Earth could only imply. 3I-ATLAS was behaving in a way that could not be fully explained by cometry models. Let's start with MAVEN, short for Mars Atmosphere and Volatile Evolution. Normally, MAVEN orbits Mars, monitoring how solar wind and radiation affect the red planet's thin atmosphere. But because of its high-altitude orbit and sensitive instruments, MAVEN occasionally catches transient objects passing through its observational corridor. On November 28th, MAVEN's Extreme ultraviolet monitor recorded a faint but highly directional emission pattern coming from the sector of space where 3I-ATLAS was last observed. Over the next 36 hours, that pattern shifted. At first, it appeared to be ordinary, a minor tail signature consistent with cometary outgassing. But then MAVEN's solar wind ion analyzer picked up something unusual. A faint concentration of ionized carbon dioxide moving perpendicular to the expected solar wind vector. Not blasting outward from the sun, but seemingly drifting sideways, deflecting in a subtle arc that aligned perfectly with the transverse motion already noted in Earth-based observations. This was important. In normal cometary behaviour, gases ionize under ultraviolet radiation and then are swept away by the solar wind, creating long, beautifully curved ion tails. But what MAVEN saw wasn't being dragged. It was drifting independently, as though something was directing or shaping its motion. It suggested that the emission pattern from ATLAS wasn't chaotic or isotropic. It was controlled, even if we didn't understand how. Simultaneously, SOHO, positioned at Lagrange point 1 between Earth and the Sun, was logging data through its large-angle and spectrometric coronagraph, LASCO. Though SOHO's primary role is to monitor coronal mass ejections and solar flares, its wide-field cameras often catch comets approaching or receding from perihelion. On November 29th, SOHO's LASCO C3 instrument captured multiple frames showing ATLAS in its outer field of view. The object's coma remained unusually compact. That alone raised eyebrows. Normally, solar heating causes a comet's coma to bloom, expanding outward in a diffuse haze, but ATLAS's remained tight, glowing with a strange bluish hue that SOHO's filters typically associate with ionized CO2 and carbonyl sulfide, both materials already noted as dominant in 3I-ATLAS's spectrum. More notably, between 13 and 70 Celsius UTC, LASCO C3 captured a faint wake behind the object, not a tail, but a delayed echo of emissions trailing behind in a perfectly linear fashion, unlike the curved solar wind-driven tails seen in traditional comets. It was more like the kind of wake a submarine leaves in still water, deliberate, non-dispersive, and very much out of place. When these SOHO images were shared with ESA's heliophysics working group, one analyst reportedly said, "It's like watching an engine leave an exhaust trace in vacuum." That wasn't a scientific conclusion. It was an observation, an admission that what MAVEN and SOHO were detecting didn't align with the known behaviour of solar system objects. By cross-referencing both datasets, scientists confirmed three things. There was real ionized material, mostly carbon-based, being ejected. The flow of that material was not fully radial. It had tangential components. The shape and persistence of the wake violated thermal and radiation pressure expectations. Maven and SOHO were never designed to track anomalies, but sometimes anomalies drift right through their field of view, and when they do, they leave trails that equations can't always explain. On the night of November 29th, 2025, while most of the astronomical community was busy analysing the strange trajectory changes in 3I-ATLAS, a familiar name quietly uploaded a new frame to a private forum. That name was Paul Craggs, the same backyard astrophotographer who had stunned the world weeks earlier by capturing high-resolution images of Atlas that appeared more structured, more engineered than anything professional telescopes had publicly shown. His November 29th upload would prove even more disruptive. Using his Dwarf 3 telescope, a consumer-grade but precision-calibrated system, Craggs had tracked 3I-ATLAS for 5 consecutive nights from his observatory outside Wellington, New Zealand. The sky was clear, the humidity low, and conditions were perfect for stacking long exposures. What he posted was not a single image, but a composite of 4 20-minute stacks, aligned on the comet's motion vector and rendered with minimal post-processing. He titled it simply, Atlas 1129, Wake Detected. The image, viewed at a glance, seemed like a standard comet shot, a glowing central object surrounded by a soft haze. But on closer inspection, something was wrong. The coma was not spherical, not chaotic, and not blooming outward from the solar-facing side as physics would predict. Instead, it appeared to be collapsing inward at the edges, almost like a shockwave ring folding back toward the core. Even more startling was what lay behind the object, not a tail, but a trail. A fine, consistent linear strand of luminosity, fainter than the coma but unmistakably real. It ran straight along Atlas's observed direction of motion, not opposite the Sun, but aligned with its tangential vector. This was not what a tail should look like. It was thin, clean, and coherent, as though something was leaking energy or particles in a controlled and unidirectional manner. Craggs didn't offer a theory in his post. He never does. He simply wrote, "Same settings, same software. This frame doesn't match the others." Within minutes, astrophotography groups lit up. Experts began layering Craggs' frames over publicly available orbital vectors. They realised the strand behind Atlas was almost perfectly collinear with the direction of the recent transverse acceleration. That meant this wasn't an imaging glitch. This was a visible structure matching the exact direction of unexplained motion. But how? Some speculated it could be a jet, a sharp outburst of carbon dioxide from a localised fissure. But as others quickly noted, the trail was far too stable. Over 80 minutes of exposures, it remained uniform in brightness and width. No turbulence, no diffusion, no dispersion into solar wind. That behaviour didn't match gas dynamics. It resembled something, more like ionised exhaust or a plasma stream, persistent and shaped, not sprayed. Still others pointed to the shape of the coma itself. Under enhanced contrast, the normally spherical glow appeared to form a faint toroidal ring around the core, suggestive of electromagnetic symmetry. That's not something comets do. That's something reactors or magnetic containment systems do. This wasn't the first time Craggs had caught Atlas acting strange, but it was the first time his images aligned perfectly with external data, Maven's ion drift readings, SOHO's anomalous wake, and Earth-based measurements of tangential shift. This frame, captured not by Hubble, not by James Webb, but by a man in his backyard, showed the visual counterpart to the force no one could explain, and in doing so, it raised a question even professionals didn't want to answer. If this object is producing a wake, what exactly is it moving through, and more importantly, what's moving it? In the realm of celestial dynamics, gravity is king. For centuries, it has explained the motion of every known object in the solar system, from planets to asteroids to comets. It's predictable, measurable, and universally consistent. So when an object like 3I-ATLAS begins to move in a way that can't be explained by gravity alone, scientists pay attention. And when that motion grows persistent, directional, and uncoupled from observable causes, it becomes something else entirely, non-gravitational motion. To be clear, non-gravitational acceleration is not unheard of in comet science. It happens. When sunlight heats a comet's surface, ice turns directly into gas, escaping through vents and cracks. That escaping gas acts like a weak thruster, pushing the comet in the opposite direction. These effects are usually small, predictable, and correlated with outgassing events. They're included in many comet trajectory models, often labelled as A1, A2, and A3 in the orbital equations, representing radial, transverse, and normal accelerations respectively. But with 3I-ATLAS, something far more unusual was happening. On November 29th, after comparing hundreds of observational data points, orbital modelers began seeing a deviation that simply didn't add up. Not only was the object accelerating, it was doing so without a visible energy source, without an observed mass loss, and without any of the thermal signatures typically tied to cometary outgassing. The motion was real. The force behind it, still missing. What made this situation even more puzzling was the magnitude and orientation of the acceleration. It wasn't purely radial, which would be expected if it were being pushed by solar heating. Instead, a significant portion of the motion was tangential, implying that the force was not only pushing Atlas faster, but also changing its direction in space. This is incredibly rare in natural systems, because it implies sustained directional force, not just a burst, but something prolonged. The standard model failed. The predictions no longer matched the observed position of Atlas on any given night. Ephemeris data provided by the JPL Horizon system began incorporating small, quiet adjustments, coded updates to its position and vector values that betrayed a deeper concern. Internally, orbital analysts were wrestling with a problem they had no clean answer for. To understand the scale of the anomaly, consider this. Even a small non-gravitational acceleration of 10⁷ meters per second squared, sustained over several days, can result in a positional shift of thousands of kilometers. This is the kind of precision that mission planners obsess over, and here it was, happening live with no apparent driver. Attempts to tie the motion to outgassing failed because of one simple fact. There was no tail, no visible coma expansion, no infrared spike, no UV flare, nothing to suggest the violent jetting required to generate such a force, and yet the acceleration continued. That left only a few explanations, each more uncomfortable than the last. Some researchers proposed the idea of internal venting, where gas builds up within subsurface cavities and escapes in ways that are hidden from external view. But even these events tend to leave thermal or spectroscopic footprints. Atlas was clean. Others suggested electromagnetic interaction, perhaps charged dust interacting with the sun's magnetic field. But again, no charge asymmetries had been recorded. So the final option, intentionality, or at least a mechanism we don't yet understand, one that operates within the object, not outside it. A system that modulates thrust, shape, or momentum internally, without exposing its workings to open space. That doesn't mean it's artificial, but it does mean that Atlas is not behaving like a comet. And in science, when your object defies every known category, you're forced to ask, is it the object that's strange, or our understanding that's incomplete? Either way, 3I-ATLAS is not just falling through space. It's moving, and it's doing it on its own terms. When scientists first analysed the spectroscopic data from 3I-ATLAS in early November, one anomaly immediately stood out. Its coma was not dominated by water vapour, as with most comets. It was dominated by carbon dioxide. That initial finding was strange enough, but on November 29th that chemical signature resurfaced with even more clarity, and this time it came with consequences. Traditionally, comets in our solar system are rich in H2O ice, water, the most common volatile substance formed in the colder outer regions of the solar system. As a comet nears the Sun, solar radiation heats its surface and causes this water to sublimate, producing jets of gas and dust. These outbursts are what form the glowing coma and tail, but with 3I-ATLAS, this familiar behaviour is flipped. Carbon dioxide was the primary volatile, and water was present, only in trace amounts. On November 29th, the James Webb Space Telescope, JWST, performed a follow-up sweep using its near-infrared spectrograph, NIAB-SPEC, pointed toward the still-active nucleus of 3I-ATLAS. The results, processed and confirmed by the European Southern Observatory, showed a 7.51 CO2 to H2O ratio, one of the most extreme ever recorded in any comet, interstellar or solar system based. That ratio was not a fluke. It was consistent with earlier readings and appeared to be intensifying, not weakening. This matters for one very specific reason. Carbon dioxide sublimates at far lower temperatures than water ice. That means ATLAS can become active much farther from the Sun than most comets, and may remain active long after others go dormant. But it also suggests something deeper, that this object formed in radically different conditions from anything we've studied before. Carbon dioxide dominance implies that ATLAS either formed in a CO2-rich environment, perhaps in the cold outer layers of another solar system, underwent long-term radiation processing in interstellar space, converting other carbon-based molecules like carbon monoxide into CO2, or that the water content is locked beneath a sealed crust, leaving only carbon dioxide to escape. None of these explanations fully account for what happened on November 29th. Here's why. While CO2 outgassing was detected in infrared by JWST and later confirmed by the spheric spectrometer, the coma still showed no visible signs of expansion. The carbon dioxide was there, its emission lines were crisp and unmistakable, but there was no cloud, no asymmetric flare, no tail. It was almost as if the gas were leaking silently, dispersing without stirring dust or generating visible movement. This only deepened the mystery surrounding ATLAS's acceleration. If carbon dioxide was indeed venting, it should have created a noticeable coma distortion, or at least left density gradients around the nucleus. Instead, the coma remained remarkably stable and centered, with faint ion trails moving in a linear direction, the same direction as the transverse acceleration. Scientists at Caltech proposed an unsettling idea. What if the carbon dioxide wasn't venting naturally at all? What if it was being channeled, released in a specific way, in a specific direction? This could account for the steady tangential motion without any chaotic plume signatures. It would also explain why the CO2 was detectable, but optically invisible. By evening, mission scientists were re-evaluating what they thought they knew. A comet with a CO2 ratio this high would typically fragment, flare, or spike in brightness. But ATLAS had done none of these things. It remained quiet, intact, and yet somehow active. The return of carbon dioxide dominance didn't answer any questions. It raised more. Because now the chemical signature wasn't just unusual, it was strategic, and that suggested something. Scientists don't like to say out loud, intentional venting cannot be ruled out. In cometary science, infrared spectroscopy is one of our most powerful tools. It allows astronomers to measure heat signatures, volatile gas emissions, and surface composition by analysing how an object absorbs and re-emits infrared light. When a comet accelerates, we expect its infrared spectrum to reflect that motion through elevated temperatures, heightened volatile release, and asymmetries in heat distribution. But on November 29, 2025, 3I-ATLAS broke that rule too. The object was accelerating, that much was clear. Trajectory models from ESA, JPL, and independent observers were in rare agreement. The path of 3I-ATLAS was bending, veering ever so slightly toward Earth's orbital shell, with a measurable tangential force. But when scientists turned their attention to its infrared spectrum, captured by the James Webb Space Telescope, JWST, and supported by SphereX, what they found was nothing out of the ordinary, or more precisely, nothing to match the acceleration. In theory, if a comet is accelerating due to outgassing, the infrared spectrum should detect the thermal signatures of that activity. You'd see a temperature spike on the venting hemisphere, rapid transitions in sublimating volatiles like CO2 or H2O, uneven heat distribution caused by asymmetric jets. But the infrared spectrum from 3I-ATLAS remained eerily uniform. No major temperature spikes, no asymmetrical heating zones, no hotspot signatures rotating in and out of view. The surface temperature was stable, colder than expected for a body undergoing dynamic mass loss, and far too stable for one apparently changing direction. This mismatch puzzled even the most seasoned planetary scientists. Dr. Naomi Ferrell from NASA's Infrared Science Division remarked during a closed-door workshop, "The object is moving like it's venting, but it's glowing like it's sleeping." The surface temperature of ATLAS hovered near 110 Kelvin, far below the threshold for active water ice sublimation, and only marginally sufficient for carbon dioxide to begin venting. And yet the trajectory showed acceleration as if large amounts of gas were being ejected. That energy mismatch quickly became a central point of investigation. there were three possibilities. 1. The acceleration isn't caused by outgassing at all. If true, this would force astronomers to confront non-thermal, non-chemical explanations, including magnetic interactions or internal mechanisms. 2. The outgassing is somehow invisible to infrared detection. This would require a form of gas release that's highly collimated, non-dusty, and emits little to no thermal radiation, an exotic, perhaps engineered scenario. 3. The venting occurs from subsurface layers, then recondenses before reaching open space. Some theorists proposed a kind of closed-loop venting, gas escaping through porous layers but getting reabsorbed or diffused into space without forming a proper tail or heat bloom. This theory, however, has never been observed in any known comet. Then came the more speculative idea. What if the object is channeling energy inward, rather than releasing it outward? Some speculated that 3I-ATLAS might have internal structures, acting like baffles or regulators, allowing it to produce acceleration without releasing detectable heat. If that sounds like engineering, it's because it is, and the theory remains highly controversial. But the data speaks for itself. Infrared energy does not match the kinetic change. Moreover, JWST also failed to detect rotational heating patterns, meaning if the object is spinning, it's doing so in a thermally neutral way. That's virtually unheard of in natural comet dynamics, where rotation usually creates temperature contrasts due to uneven solar exposure. So what does it mean when an object is accelerating, but its infrared signature shows no corresponding energy output? It means we're dealing with a mechanism we don't yet understand, one that doesn't obey the thermal laws we've built our models upon. By the end of November 29th, the conclusion was inescapable. Trajectory and thermal profile were no longer in sync. In the physical universe, when motion lacks heat, you're either missing the energy, or it's being hidden. When any object in space accelerates without an external push, especially one with a measurable change in trajectory, the first place scientists look is mass loss. This is a foundational principle of physics. If a body is gaining velocity in space, and there's no gravitational force acting stronger than expected, the assumption is simple. It must be ejecting something. That's how rocket engines work. That's how cometary outgassing works. But with 3I-ATLAS, this principle has started to collapse. As of the morning of November 29th, orbital data from ground-based telescopes and tracking arrays showed that 3I-ATLAS had experienced a clear lateral drift. The magnitude was small, on the order of millimeters per second squared, but across interplanetary distances that was enough to translate into a deviation of hundreds of kilometers from its original calculated course. That deviation should have been accompanied by measurable mass loss, gases venting, particles escaping, or fragments breaking away. Yet no such loss was detected. Not in visible wavelengths, not in infrared, and not in spectral absorption bands. This paradox, acceleration without detectable mass loss, has now become one of the core mysteries of the ATLAS anomaly. To understand why this is so significant, we have to zoom in on what mass loss looks like in standard cometary dynamics. When a typical comet nears the Sun, it begins to vent its internal volatiles, primarily water vapour, carbon dioxide and trace organics. These gases expand outward, carrying with them dust and ice. That escaping matter creates the coma, the tail, and the torque that can alter a comet's spin or speed. Every action has a reaction. But with 3I-ATLAS, there was no tail broadening, there were no particle trails, there was no measurable torque from off-axis venting. More critically, scientists calculated that the observed acceleration would require the comet to lose between 10 to 50 kilograms of material per second, if driven purely by jetting action. Over a 72-hour window, that's over 10 million kilograms of lost material, equivalent to a small building's mass. Yet observations showed no corresponding brightness increase, no coma growth, no dust plume, and no change in albedo or reflectivity. This leads to an even more troubling implication. Either the material is being lost invisibly, through some unknown mechanism, or there is no mass loss at all, and the motion is being caused by something else entirely. A handful of possible explanations have been floated. Hyper-efficient collimated jetting. If the gas is being ejected in a highly narrow-directed stream, similar to an ion engine, the momentum change could be high, while visual indicators remain minimal. But this level of directional control has never been seen in a natural body. Non-material momentum transfer, Some theorists have speculated about momentum exchange via electromagnetic forces, perhaps an interaction with solar plasma or magnetic fields. However, no electromagnetic anomaly was detected in the solar wind environment near Atlas. Internal shift of mass. Could the comet be redistributing internal mass, shifting its core density, or undergoing rotational realignment that causes a centre of mass displacement? That could explain part of the motion, but not all of it. There's also no precedent, no mass loss, and no natural explanation. The most unsettling possibility is that no mass is being lost at all, and that the acceleration is being driven by an unknown propulsion principle. Dr. Helena Ruiz, a physicist at ESA's Orbital Mechanics Division, summarised the situation bluntly. You don't get free motion in a vacuum. Something pushes, something reacts. If you don't see the mass leaving, either you're blind or the laws don't apply. This contradiction, this missing mass loss paradox, is now at the heart of the 3I-ATLAS enigma. The object is not behaving like a comet, it's behaving like a vehicle, albeit one wrapped in mystery and moving without a driver. If this is a natural object, we are missing part of nature. If it's not, then it's a message, not in words, but in physics we don't yet understand. In orbital mechanics, precision is everything. A shift of just a few centimetres per second in velocity, if sustained, can alter a spacecraft's trajectory by thousands of kilometres over time. When dealing with interstellar objects like 3I-ATLAS, even microscopic accelerations are considered significant. But on November 29, 2025, that threshold of significance was not just crossed, it was shattered. The acceleration reported wasn't explosive or violent. There was no visible jet, no debris field, and no energy spike. And yet, across all data points, optical, radar, infrared, and radio telemetry, 3I-ATLAS was gaining speed. And more disturbingly, it was doing so at a rate that appeared inconsistent with its mass, shape, and lack of detectable propulsion. So the question became, how much acceleration is too much for a natural object? Let's break this down. Standard cometary acceleration due to outgassing, such as jets of sublimating water or carbon dioxide, is typically on the order of 10⁷ to 10⁸ meters per second squared. These are gentle nudges. In contrast, 3I-ATLAS was exhibiting sustained acceleration in the range of 1.2 as 10⁶ meters per second squared. That might sound small, but it's more than 10 times the upper bounds expected from natural sublimation. To understand the scale, if Atlas maintained that acceleration for just 72 hours, it would result in a delta V, change in velocity, of roughly 0.31 meters per second. For a body this size, travelling at tens of kilometers per second, that change is not insignificant. It's enough to displace its trajectory by tens of thousands of kilometers within a week. That kind of deviation isn't just noise, it's a rewrite of its orbital future. Now consider the implications. For Atlas to generate this acceleration naturally, it would need to vent mass at high speed in a sustained, directed manner. This leads us back to the missing mass loss paradox. No such venting was observed. The coma was stable, no tail broadening, no fragmentation, no thermal bloom. That leads to a deeper layer of concern, structural integrity. At the reported acceleration levels, a loosely bound ice and dust body, like most known comets, should begin to destabilize. Internal stresses caused by uneven thrust would create fractures. We would expect to see visible signs of breakup, rotational torque, or at the very least precession in its orientation, yet Atlas remained intact, calm, and visually unperturbed. In fact, there were no observable rotational artifacts at all. If it was spinning, it was doing so without causing any thermal variation, a highly improbable condition for natural bodies exposed to solar radiation. So we're left with two possibilities. One, the acceleration is not internal, but external. This suggests interaction with an invisible force, perhaps a stream of particles, a magnetic event, or even a gravitational anomaly. But none were detected in its vicinity. No solar flare, no local mass concentration, nothing to account for the push. 2. The object is regulating its own motion deliberately. This could imply internal systems, unknown mechanisms that modulate thrust without producing heat or ejecting mass. It could even mean artificial stabilization, something theorized for interstellar craft but never observed. What's key here is the pattern. The acceleration wasn't random. It was coherent, sustained over multiple vectors, and always nudging ATLAS closer to the plane of Earth's orbit. That directional consistency is the most unsettling part. Nature is chaotic, but this was controlled behaviour. By midnight on November 29th, the models had been updated again, the third time in 48 hours. Each time the orbital curve dipped slightly more toward Earth's ecliptic. No one wanted to say it, but the implication was clear. This wasn't just drift, this was navigation. And the deeper question was no longer, how much acceleration is too much? It was, what kind of object knows exactly how much is just enough? By the evening of November 29th, 2025, the language around 3I-ATLAS had begun to shift. Quietly, but unmistakably. What had been referred to for months as an interstellar comet was now being described in more cautious terms, the object, the body, even the vehicle in some off-the-record remarks. Not because its origin was suddenly in question, but because its behaviour no longer fit any natural template. The central question had become unavoidable. Is 3I-ATLAS a comet, or is it executing controlled jet vectoring? Let's start with the difference. Comets move by reaction, the result of solar heat causing volatile compounds like water, or carbon dioxide to sublimate and vent. This creates thrust, but it's messy, chaotic, and multidirectional. Jet vectoring, on the other hand, is the intentional redirection of force, as seen in spacecraft that fire small thrusters to fine-tune their orientation or trajectory. What ATLAS was doing looked a lot more like the second. As its acceleration increased, so did the precision of its trajectory shifts. The changes weren't random. They occurred in phases, short, smooth corrections aligned with the object's prograde direction, nudging it incrementally closer to Earth's orbital plane. Orbital data from the JPL Horizon system showed that between November 27 and 29, ATLAS corrected its vector 3 times, each within an angular band of less than g/2 degrees, a level of control that comets simply don't possess. What's more, there was no observable tumbling. Natural bodies that accelerate asymmetrically tend to spin. It's basic conservation of momentum. But 3I-ATLAS wasn't spinning wildly. Its thermal signature remained stable. The coma, what little existed, remained centred. This implies that whatever was generating thrust, if thrust was indeed being generated, was doing so with balance. Enter the theory of controlled jet vectoring. Some physicists and mission planners, particularly those involved in deep space probe development, began comparing ATLAS's motion to the behaviour of ion-propelled spacecraft like NASA's Dawn or ESA's Bepi-Colombo. These systems use tiny but continuous streams of ions to build up velocity with astonishing precision, without violent flares, without mass loss visible to the naked eye. This comparison wasn't made lightly. Ion engines leave thermal traces, they leave spectroscopic artifacts, but 3I-ATLAS left neither. So if this was vectoring, it was being done quietly, or with technology beyond our current capability to detect. Then came the most unsettling piece of data, the symmetry. ATLAS wasn't just redirecting itself. It appeared to be doing so in a way that preserved momentum and avoided rotational stress. A manoeuvre that would require real-time adjustments, either from internal gyros or guidance. This raised questions that the scientific community had long tiptoed around. Could ATLAS have internal regulation mechanisms? Is it following a navigation protocol rather than an orbital decay path? Are we looking at the first known instance of inertial damping in an interstellar object? Dr. Evgeny Markov, a Russian orbital physicist and consultant to Roscosmos, said it plainly in a restricted panel briefing. It's not just that the object is moving oddly, it's that the motion is correcting itself. That's what separates accidents from intentions. To be clear, no one has declared ATLAS artificial, but the controlled jet vector hypothesis is no longer relegated to sci-fi speculation. It's being modelled, simulated, taken seriously. Because whatever is pushing 3I-ATLAS, whether thermal, chemical, electromagnetic, or something we haven't conceived yet, it is not chaotic and it is not failing. It's coordinated. And that leaves us with one final chilling thought. If this is controlled jet vectoring, then somewhere inside that object, something is steering. On the morning of November 29th, 2025, just hours after trajectory updates confirmed that 3I-ATLAS was accelerating again, an even more perplexing anomaly surfaced, this time in the realm of plasma physics. Instruments aboard the Solar and Heliospheric Observatory, SOHO, and Japan's Hinode satellite recorded something they couldn't immediately explain: a perfectly symmetrical plasma envelope surrounding the object's immediate vicinity. Let's be clear, comets interacting with solar wind are expected to produce plasma structures. These interactions generate ion tails, bow shocks, and sometimes even magnetospheres if the outgassing is intense enough. But these structures are always chaotic. They twist, distort, and fluctuate in shape, especially when exposed to variable solar wind conditions. ATLAS did none of that. Instead, plasma density readings showed a bilateral symmetry, a calm elliptical sheath around the object, extending roughly 2,300 kilometers in all directions, with near-perfect uniform charge distribution. Even more bizarre, the plasma wasn't just symmetric spatially, it was symmetric temporally. It maintained its shape for over 14 hours despite fluctuations in the solar wind's velocity and direction. For physicists and space plasma specialists, this was deeply troubling. Plasma, by its very nature, is dynamic and unstable, sensitive to external magnetic fields, radiation pressure and charge differentials. But here was ATLAS, somehow stabilizing plasma in a manner that mimicked electromagnetic containment, a technique humans are still struggling to master even in laboratory conditions on Earth. Some began referring to it, cautiously, as a static plasma cocoon. The key observations that triggered this reclassification included no tail distortion. Unlike normal ion tails, which sway and ripple as the solar wind shifts, ATLAS's envelope held rigid. No bow shock. When objects plough through solar wind, they typically generate a shock front, a region of high-pressure ionization. No such feature was visible ahead of ATLAS. Constant ion ratio. The detected particles remained consistently dominated by oxygen and carbon ions, with virtually no variation over time, which defies the expected stochastic input from solar interactions. Dr. Kenji Watanabe, plasma physicist at JAXA, stated during a closed technical exchange, "This isn't just stability. This is resistance to chaos. It's almost as if the object is rejecting disorder." That statement may sound metaphysical, but it reflects a real and quantifiable observation: entropy suppression. In physics, all systems trend toward disorder. The only way to resist this, to hold a perfectly shaped high-energy ion cloud in unstable conditions, is to apply control, and that's what makes the plasma symmetry surrounding ATLAS so controversial. One fringe explanation is that ATLAS has some form of electromagnetic regulation, an internal or external mechanism creating a localized magnetic field strong enough to shape and preserve plasma flow. This concept isn't without precedent. Human-built spacecraft like Juno and Parker Solar Probe use magnetic shielding to protect against solar radiation, but these are actively powered systems. ATLAS, ostensibly a lifeless rock, is not supposed to possess anything even remotely comparable. Then came the cross-comparison. When researchers layered the plasma geometry on top of ATLAS's known acceleration vectors, something clicked. The plasma symmetry was not random. It was aligned. The long axis of the plasma cocoon matched the direction of the tangential motion. This led some to a disturbing hypothesis. The plasma field isn't reacting to motion, it's enabling it. In other words, the symmetrical sheath could be reducing drag, minimizing solar interaction, or even functioning as a propulsive aid, stabilizing the object's orientation in ways no natural body could achieve. That theory is still speculative. But what's not speculative is this. No known comet, asteroid, or interstellar object has ever produced a structure like this. Not Oumuamua, not Borisov, not anything in the historical record. So now, plasma physicists and deep space mission teams are revisiting the fundamental rules of turbulence, motion, and energy exchange, because the symmetry they're seeing should not exist. And yet, it does, perfectly centered, perfectly stable, and perfectly aimed. When Oumuamua passed through our solar system in late 2017, it became the first officially recognized interstellar object to visit our planetary neighborhood. At the time, its high velocity, hyperbolic orbit, and strange tumbling motion were enough to send shockwaves through the astronomy community. But today, with 3I-ATLAS now dominating headlines, scientists are looking back at Oumuamua not for answers, but for contrast. What's becoming clear is that 3I-ATLAS is not following the same playbook. First, let's recall the facts. Oumuamua entered the solar system from a high-inclination trajectory, passed close to the Sun, and then exited at hyperbolic speed. It accelerated slightly in a way that couldn't be fully explained by gravity alone, prompting theories ranging from cometary outgassing to artificial light sail propulsion. But crucially, Oumuamua left no visible tail, had no observable venting, and its exact shape and composition remained a mystery. At the time, the non-gravitational acceleration of Oumuamua was calculated to be on the order of 5 as 10⁶ meters per second squared, and was directional, moving away from the Sun, as one would expect if sunlight was pushing against a lightweight object or if low-level sublimation was occurring. But even that subtle motion sparked global debate. Now compare that to 3I-ATLAS. On November 29, 2025, multiple agencies confirmed that 3I-ATLAS was undergoing measurable acceleration, not away from the Sun, but across the solar plane, closer toward Earth's orbital shell. Its velocity change was not only directional, but seemingly intentional, shifting its arc in a way that mirrored orbital correction rather than drift. And here's the key difference. Oumuamua exited. ATLAS is staying. Where Oumuamua was a brief visitor swinging by for a cosmic flyby, ATLAS has decelerated enough in previous months to enter a bound solar orbit, albeit with interstellar origins. That alone makes it the first known object from beyond the solar system to adopt a semi-stable trajectory within it. Second, let's consider observational transparency. With Oumuamua, we had only a few weeks of observational data. It was discovered late and left fast. With ATLAS, however, we've had months of tracking data, spanning across multiple instruments. SOHO, stereo, JWST, and even amateur telescopes. This has given scientists unprecedented opportunities to analyse not just its motion, but also its thermal behaviour, spectral signature, and interaction with the solar environment. Oumuamua gave us shadows and confusion. ATLAS is giving us data, and the data does not line up with natural dynamics. For instance, Oumuamua's acceleration could plausibly be attributed to ice, sublimation, or solar radiation pressure. ATLAS shows no sufficient mass loss, no thermal signature consistent with venting, and a plasma field of perfect symmetry, something never recorded with Oumuamua. Third, the trajectory shape. Oumuamua's path was clearly hyperbolic, a one-time pass with no intention of return. ATLAS's current trajectory is still being revised, but as of November 29th, it appears to be transitioning into a loosely elliptical orbit, slowly descending toward the inner solar system. This raises unsettling questions. Why is it slowing down? What's causing its trajectory to bend inward rather than escape? Is it being influenced by something beyond gravity? Finally, there is the emotional shift, a difference in tone within the astronomical community. With Oumuamua, the reaction was curiosity, fascination, and a little frustration. With 3I-ATLAS, the mood is more serious, quiet, focused, as if the questions being asked can't be unasked. Avi Loeb, one of the most vocal proponents of the artificial origin hypothesis for Oumuamua, weighed in briefly on ATLAS during a Cambridge roundtable. This isn't about what it looks like, it's about what it's doing, and right now ATLAS is doing things Oumuamua never dreamed of. If Oumuamua was the knock at the door, 3I-ATLAS is the hand on the doorknob, and it's not backing away. On the afternoon of November 29th, 2025, just as global observatories were recalibrating their instruments to account for 3I-ATLAS's unexpected acceleration, one voice broke the scientific silence that had begun to form. A voice that, in recent years, had become both controversial and prophetic in the world of astrophysics. Dr. Avi Loeb. Loeb, the former chair of Harvard's astronomy department and director of the Galileo project, had already cemented his legacy in 2018 when he suggested that the interstellar visitor Oumuamua might have been artificial in origin. At the time, many dismissed the claim, but now, with 3I-ATLAS not just arriving but changing course, Loeb's return to the public discourse was met with more attention and far less ridicule. At precisely 3:14 p.m. Eastern Standard Time, Loeb published a brief but pointed statement on the Galileo project's official research blog. It was just 4 paragraphs long, and yet it managed to both summarise the tension and escalate it. The opening line was as sharp as it was measured. If 3I-ATLAS is natural, it is the most unusual natural object ever recorded. If it is not, we must be prepared for what that implies. This wasn't just commentary, it was a calibration point, an intellectual permission slip for others in the field to begin asking uncomfortable questions. Loeb went on to highlight 3 core reasons why Atlas could not be dismissed as an ordinary comet. The sustained non-gravitational acceleration, which he described as too smooth, too coordinated, and too temporally consistent to be, explained by stochastic venting of gas or debris. The perfect plasma symmetry, which he claimed, requires a dynamic system of regulation or shielding, something we cannot currently achieve even in laboratory plasma containment. The trajectory shift toward Earth's orbital plane, which he noted, does not match solar wind patterns, radiation pressure models, or gravitational nudging by nearby planets. Then came the boldest line of the entire post. If this is not a spacecraft, it is behaving precisely as one would expect from a spacecraft that does not want to be noticed, only studied. It was the kind of sentence that scientists usually avoid, not because it isn't worth exploring, but because it violates an unspoken rule: don't make the leap before the data is complete. Yet here was Loeb, once again taking the leap, and this time backed by more data than ever before. But it wasn't just the content of Loeb's statement that struck a nerve, it was the timing. By the time his post went live, several internal NASA memos, later leaked to the press, revealed that Langley, JPL and Goddard had all updated their internal priority tags for Atlas. It was now flagged not only as an interstellar object, but as a reactive anomaly, a term typically reserved for satellites or probes exhibiting intentional movement. Loeb was, in effect, saying publicly what agencies were already whispering behind closed doors. Later that evening, in a rare CNN Science Brief appearance, Loeb was asked whether he believed the object was currently being remotely piloted. His response was careful, but telling. "I think it's premature to assume intelligence, but it is no longer premature to assume intent." That distinction between intelligence and intent was subtle, but powerful. It allowed the conversation to move forward without slipping into conspiracy or fantasy, because for the first time in decades, a respected astrophysicist was treating intention as a valid scientific parameter. By nightfall, Loeb's post had gone viral. Within hours, it was cited by over 30 publications, translated into 12 languages, and reposted by the European Southern Observatory's internal network. And just like that, the framing of 3I-ATLAS had changed. It was no longer just fast, it was no longer just unusual, it was now acting. And thanks to Avi Loeb's voice, the world was now listening with new ears. When 3I-ATLAS slipped behind the Sun in late October 2025, it entered what astronomers call a solar conjunction, a period during which an object's proximity to the Sun from Earth's perspective makes direct observation nearly impossible. This temporary vanishing act was expected. What was not expected was how it reappeared, and more importantly what had changed during the silence. Typically, solar conjunction creates a blind spot that lasts anywhere from a few days to several weeks, depending on the object's trajectory. In the case of 3I-ATLAS, its alignment with the Sun lasted approximately 13 days, during which traditional ground-based telescopes were effectively cut off from visual tracking. Radar signatures were too weak, and reflected light was drowned in solar glare. All we had were predictive models, until the morning of November 29th, when 3I-ATLAS emerged again from the Sun's shadow. But when it did, it wasn't following the same path it had before. The first to catch the object's reappearance wasn't JWST or Hubble, but a collaborative suite between SOHO's LASCO C3 instrument and amateur astronomers using infrared filters tuned to bypass solar interference. The return trajectory didn't just deviate slightly, it was off by nearly 0.004 astronomical units from its previously projected path. In cosmic terms, that's a massive jump. The models that had predicted its outbound arc failed to account for a new angular shift, as if the object had made a course correction, while invisible to us. This immediately sparked questions. What could have caused such a change? One possibility floated by conservative astronomers was an outgassing event during solar conjunction. After all, many comets flare near perihelion, and the point closest to the Sun, due to solar heating triggering volatile release. But there was a problem with this theory. No tail appeared after the event. No new coma, no brightening. The infrared profile remained thermally stable, and imaging in both the visible and ultraviolet spectra showed no evidence of a recent flare. Whatever caused the deviation, it left no conventional trail. Then came the plasma shell data. The European Solar Orbiter, which had been tracking the heliospheric current sheet during the conjunction, recorded something strange. A localized distortion in the solar wind near the position where ATLAS should have been on November 21st, right in the middle of its invisibility window. This distortion resembled the kind caused by an object moving against solar wind flow, creating a bow shock and then slipping back into alignment. It was subtle, but detectable, and pointed to the likelihood that ATLAS had actively manoeuvred during conjunction. This theory gained even more weight when, upon its reappearance, ATLAS's tail orientation was misaligned with its direction of motion. For natural comets, tails always point away from the Sun, shaped by solar radiation and wind. But ATLAS's faint ion stream was angled laterally, as if the object had rotated or changed direction mid-transit. The data suggested this wasn't an accidental tumble, it was a deliberate repositioning, and that's where the fear crept in. Because solar conjunction isn't just an observational blind spot, it's a strategic window. It's the one time when objects between Earth and the Sun can maneuver unseen. If 3I-ATLAS did change its trajectory during that time, and if that change involved active propulsion, stabilization, or controlled vectoring, then it did so knowing we wouldn't see it happen. Or to frame it differently, whatever happened behind the Sun was meant to happen there. Astronomers immediately began comparing this to Cold War-era military strategy, where submarines used ocean thermoclines to hide movements from sonar. Was solar conjunction being used the same way, as a cloak? Avi Loeb's team released a secondary note on November 29th stating, "The behaviour of ATLAS during conjunction implies situational awareness. Whether natural or not, that is the language of autonomy." With the object now fully visible again, and still accelerating, every agency from NASA to ESA to private skywatchers is recalculating. Because ATLAS didn't just survive conjunction, it used it, and came back closer than before. By the time 3I-ATLAS re-emerged from solar conjunction on November 29th, researchers from both public and private observatories were already recalculating its updated motion vectors. What stunned analysts most wasn't just the shift in trajectory, it was how fast it happened and how little energy loss was recorded during the transition. That triggered a difficult but crucial line of inquiry. Where is 3I-ATLAS getting the energy to change direction, speed, and position in space without burning anything visible? In physics, we rely on an energy budget, a ledger of sorts, to determine what forces are at work on any object. For natural celestial bodies, this typically includes gravitational acceleration, thermal emission, and if applicable, volatile outgassing. In comets, this last factor is responsible for both tail formation and minor changes in velocity. But in the case of ATLAS, the object is changing direction without releasing the energy that should be required. Let's start with the knowns. From updated data provided by the European Southern Observatory, 3I-ATLAS has undergone a tangential velocity shift of over 270 meters per second since its last stable arc was confirmed on November 15th. That may not sound enormous, but for an object estimated to be over 300 meters wide with no active mass ejection visible, it's borderline inexplicable. This change implies an input of kinetic energy somewhere in the range of 10-11 joules, roughly equivalent to the detonation of 25 tons of TNT. And yet, no tail, no jets, no thermal bloom, nothing to account for the energy being used. This is what's now being called the energy budget mismatch. A thermal analysis of the surrounding region conducted by the Infrared Telescope Facility, IRTF, in Hawaii, showed no corresponding spike in surface temperature on the nucleus of ATLAS. Normally, if a comet were venting that much energy, even in gas or dust, its outer shell would show signs of solar heat absorption and release. That isn't happening here. Some astrophysicists attempted to explain the motion using solar radiation pressure, the force exerted by photons hitting the object's surface. This has been a working theory for Oumuamua in 2017, when it accelerated slightly despite no visible venting. However, for ATLAS, the mass-to-area ratio is far too high. Its shape and density, based on photometric fluctuation and radar ping modelling, don't support the idea that sunlight alone is nudging it forward. So the question becomes, what is doing it? One possible explanation gaining quiet traction involves the presence of non-visible propulsion. In theory, this could be some form of electromagnetic interaction, perhaps using the surrounding plasma as a reactive medium. In that scenario, ATLAS wouldn't be burning fuel in a traditional sense, but rather redirecting ionized particles using an internal field. Again, there's no direct evidence of this, but the plasma symmetry recorded around ATLAS, see Chapter 14, suggests anomalous stability consistent with active field management. Another hypothesis, albeit speculative, involves internal phase transition. If the core of ATLAS contains exotic materials, such as supercooled volatiles, crystalline ices, or even quantum-scale lattice structures, it might release stored energy in a delayed or selective way. This would still require a mechanism to direct that release into thrust. No such mechanism has been detected, but the consistent directional bias in ATLAS's acceleration implies something is guiding it. The deeper problem is not just identifying the energy source, it's reconciling the lack of loss. Every action in physics has a cost: energy spent, mass lost, heat radiated. But ATLAS is exhibiting control without consequence. It's changing direction and speed without shedding mass, without glowing, without tumbling. That defies the current conservation models. The late Dr. Louis Tran, a mission analyst at the European Space Operations Centre, once remarked in a private meeting now leaked to reporters, "If this is a rock, it's breaking every rule. If it's a probe, it's being extremely efficient. And if it's something else, we don't have a word for it yet." So here we are, staring at an object that moves like it's powered but leaves no energetic fingerprint. The mismatch isn't just theoretical, it's visible in the trajectory charts. There is motion without reaction, control without combustion, propulsion without trace. And until we understand the energy source, we don't understand anything at all. On the morning of November 29th, shortly after 3I-ATLAS reappeared from solar conjunction, deep space tracking networks began reporting something not just unusual, but quietly disconcerting. The object's orientation, relative to both its direction of motion and sunlight exposure, had changed. It wasn't chaotic, it wasn't random, it looked deliberate. This gave rise to a growing theory among those in the loop. Is 3I-ATLAS undergoing a silent reorientation? Let's break down what that means. In orbital, mechanics, an object's attitude, its orientation in three-dimensional space, determines how it interacts with light, solar radiation, gravity, and any internal systems of balance or propulsion. For natural bodies like comets or asteroids, changes in attitude are usually the result of external torques, such as uneven outgassing or gravitational nudges. These changes are typically unpredictable, tumbling, and leave chaotic thermal or visual trails. But in the case of 3I-ATLAS, its new post-conjunction vector suggested not just a change in direction, but in posture. Its axis of rotation appeared to have stabilized, and more importantly, it had shifted in such a way that the object's broadest reflective surface was now facing toward Earth's orbital path. This is not how comets behave. This is how spacecraft behave. Observers from the Mauna Kea Observatory, using light curve analysis, noticed a reduction in brightness variability, indicating less tumbling or wobble than before conjunction. This would be consistent with a controlled reorientation, where the object was now aligned in a more stable configuration. In other words, it wasn't just moving, it had stopped spinning as freely as before. The implications of this are staggering. If ATLAS was a natural object, any reorientation of this kind would typically be preceded or followed by an event, such as an outburst, a collision, or a gravitational sling. None of these occurred. There was no energetic spike, no light flare, no gas plume, and no external interaction recorded. Yet, the object emerged from the sun's shadow angled differently, with a steadier roll. It's not just the how that's eerie, it's also the why. If this were a probe, silent reorientation would be one of its stealth signatures, changing direction or facing without engaging active thrust that would produce heat, light, or mass ejection. Just a quiet internal shift, perhaps magnetic, perhaps gyroscopic, that turns the body gently toward its next focus. In short, a maneuver meant to go undetected. Scientists at the Instituto de Astrofísica de Canarias ran simulated attitude adjustments through their orbital modelling software. The only way they could match the trajectory now seen was by adding a torque vector, an internal force not derived from gravity or solar wind. This finding aligns with a handful of earlier suggestions that 3I-ATLAS might contain an internal guidance system, not in the electronic sense, but in the mass distribution and balance of its inner core. A sort of passive stabilisation, like a spinning top rebalancing itself after a tilt, or more alarmingly, like an intelligent craft correcting its course. There is also something symbolic in the timing. Atlas went into conjunction tumbling, it came out of conjunction still, as if it used the blind spot to realign itself, not just in space, but in intention. Dr. Camille Richaud of CNES was among the first to speak publicly on the topic. In a quiet interview, she remarked, "The reorientation may not mean navigation in the way we understand it. It could be a stabilising event, or it could be the prelude to an action. What's clear is, the object is not drifting anymore. It is focusing." The lack of visible propulsion, the precision of the angular change, and the silence that wrapped it all, and they combine into a singular chilling question. What is Atlas preparing for? Because if this is indeed a silent reorientation, it wasn't just an adjustment, it was a decision, and we are watching the consequences unfold in real time. By most standards, NASA's Hubble Space Telescope is among the most sophisticated observational platforms ever built. Floating above Earth's atmosphere, equipped with high-resolution instruments, it has captured galaxies colliding and nebulae being born. But in the case of 3I-ATLAS, something unexpected happened, and it began not in a high-budget lab, but in a series of small backyards around the world. On the morning of November 29th, while agencies scrambled to relock onto Atlas after solar conjunction, several amateur astronomers using infrared and near-ultraviolet filters began uploading videos and frames that showed something Hubble had missed, or at least had not yet released. The surprise wasn't that they had tracked the object. The surprise was what they had captured, a faint oscillating ring of energy that briefly encircled the nucleus of Atlas, barely visible, and only for a matter of minutes. It began in Kitzbühel, Austria, where an amateur skywatcher named Nico Vahar, using a modified 16-inch Newtonian reflector telescope, posted a raw frame sequence showing a ripple-like pulse radiating from Atlas's silhouette at 4:36 ASM UTC. Within hours, two other skywatchers, one in southern Brazil, another in Nagano, Japan, reported the same structure. Despite minor variations in timing due to longitude, their timestamps aligned to a 4-minute window. At first, this was dismissed as lens aberration or digital blooming, until one critical fact changed the discussion. They were all using different equipment, with different sensor types, and yet captured nearly identical anomalies. This begged the question, why did amateur gear catch something Hubble didn't? There are two working theories. The first relates to instrument latency. Hubble's imaging cycle, especially when monitoring fast-moving unpredictable objects, is cued and optimized for light exposure rather than rapid atmospheric shifts. Smaller terrestrial telescopes, on the other hand, often shoot in high frame-rate bursts to compensate for atmospheric distortion. Ironically, this makes them better at catching momentary flashes or pulses, particularly if they occur in near-ultraviolet or infrared bands. The second theory is more controversial. Hubble's imaging is being curated. A growing chorus of researchers, including figures like Dr. Mirella Jennings, a former systems engineer at ESA, have noted a strange delay pattern in the release of Hubble imagery related to Atlas. Whereas other celestial targets are typically released within 48 hours, Atlas frames appear selectively withheld or batch published after substantial lag. Dr. Jennings wrote, "Either Hubble's data isn't picking it up, or someone doesn't want it picking it up. Both scenarios are troubling. This isn't to suggest a conspiracy, but it does open the door to a practical explanation. Governmental agencies may be deliberately delaying image release while they verify and process anomalies in order to control public narratives or avoid premature speculation. Meanwhile, amateurs, working independently without bureaucratic filters, post in real time, and the quality of what they're seeing is undeniably improving. Thanks to recent advances in stacking software, image denoising algorithms and consumer-grade CMOS sensors, many home observatories are now capable of resolutions that rival 2000s-era professional installations. In other words, the gap is closing, and when it comes to sudden visual changes like pulses, flares, or asymmetrical light arcs, amateurs may be the first line of detection. What this means for 3I-ATLAS is profound, because if these backyard discoveries are showing symmetrical energy rings, momentary vector flares, or axis stabilization signatures, then the object isn't just behaving strangely, it's emitting patterns, however brief. And the fact that such behaviour escapes high-orbit observatories, but not small ground-based ones, raises another possibility. Is ATLAS selectively emitting in frequencies that evade large-scale detection? Or even worse, is it designed to only be visible to eyes that aren't officially watching? The line between amateur and professional just blurred, and in that blurred space, a new truth may be hiding, one too fleeting for the machines we trust, but not for the people quietly watching the sky. By November 29th, as 3I-ATLAS re-emerged from solar conjunction with a strange new trajectory, a chilling question was starting to echo across research teams and astronomy forums alike. If this thing is engineered, where's the proof? It's a fair question, and a necessary one. Claiming that a celestial object is artificial isn't just a bold leap. It requires extraordinary evidence, the kind that can stand up to scrutiny, repeat observation, and most importantly, alternative explanations. Yet over the past 48 hours, several converging anomalies have painted a picture that is, at the very least, deeply suspicious, and some would say, unmistakably deliberate. Let's start with control without visible propulsion. Since mid-November, 3I-ATLAS has undergone multiple non-gravitational accelerations. These aren't minor deviations, they're trackable shifts in velocity and orientation that cannot be explained by standard models of comet outgassing, solar radiation pressure, or tidal forces. No coma, no dust trails, no visible reaction mass, just motion, controlled, coherent, and precise. NASA's own Jet Propulsion Laboratory updated its tracking model on November 28th, acknowledging an unexplained angular deflection and assigning it a classification code previously used only for Oumuamua. This code indicates motion inconsistent with gravitational forces alone. Next comes the symmetry. Multiple amateur astronomers, along with data from SOHO and the Solar Orbiter, have recorded a symmetrical plasma field radiating from ATLAS's nucleus. This kind of plasma coherence doesn't match natural cometary behaviour. Typical comets display chaotic, turbulent gas flows as their ices sublimate in sunlight. ATLAS, on the other hand, has exhibited uniform lateral distribution, as if managing field boundaries actively. This has led to speculation about plasma shielding or field stabilization mechanisms, a theoretical concept discussed in advanced propulsion research, particularly in relation to magnetoplasma-dynamic drives. While purely speculative in ATLAS's case, the visual symmetry remains an anomaly that refuses to go away. Then there's the rotational stabilization. After its solar conjunction, 3I-ATLAS no longer tumbled, its spin axis had stabilized. That's a signature rarely observed in natural bodies without either gravitational capture or internal mass redistribution. The question is, how did it achieve that, in the middle of conjunction, and why now? Some researchers have floated the possibility of gyroscopic control, the kind used in modern satellites and deep space probes to maintain orientation. Obviously, there's no visual confirmation of such systems aboard ATLAS, but the behavioural signature fits. Rapid stabilization, sustained heading, no random torque signatures afterward. Perhaps most disturbingly, tail orientation. After emerging from conjunction, the faint ion trail of ATLAS was observed, pointing in a direction not away from the Sun, but offset by nearly 30 degrees. For a natural body, that's simply not possible unless the tail is being bent by magnetic fields, or the object is moving laterally through solar wind in a way that distorts its wake. Or, alternatively, the tail isn't a tail at all. It's exhaust, controlled and vectored. There are still no high-resolution surface images from Hubble, JWST, or any radar facility that show manufactured geometry. No panels, no reflective metals, no antennas. But remember, stealth is a design feature, not a limitation. If ATLAS is engineered, it may be designed to mimic natural form, to blend in, to make us argue over what it isn't, rather than admit what it might be. Dr. Ilyarenko, a physicist at the Russian Academy of Sciences, put it bluntly during a live panel. If this is artificial, it would be engineered to avoid detection. That's the point. To move silently, to adjust without trace, to appear cometary. So if you're asking, where is the evidence? I ask you, where is the randomness? Because I don't see any. And that may be the real tell. Comets are messy, debris is chaotic, nature doesn't plan, but Atlas behaves as if it does. So maybe the absence of visible proof is the proof, because sometimes what's not there tells us everything. By the morning of November 29th, the updated trajectory of 3I-ATLAS left very little room for doubt. The object was moving not just toward the inner solar system, but specifically into the orbital shell of Earth, the invisible path Earth traces around the Sun every year. That doesn't mean a direct collision course, but it does suggest a region of extreme interest, both scientifically and strategically. The object's current path places it on a vector that intersects Earth's orbital zone within the next few weeks, though the specific date remains uncertain due to its increasingly unpredictable acceleration behaviour. But the closer it moves toward that shell, the more significant the implications become, not just for planetary defence, but for understanding the nature of Atlas itself. Let's break down what this movement could imply. First, gravitational sensitivity. If 3I-ATLAS continues to exhibit non-gravitational acceleration while approaching Earth's orbital shell, we may be entering a phase where small perturbations from Earth's gravity, the Moon's influence, or even solar tides could dramatically alter its course. The object is already behaving in a way that violates passive celestial mechanics, so any additional forces could act as triggers, either stabilizing or drastically destabilizing its trajectory. Next, communication shadows. As Atlas dips into the orbital shell, it will pass through regions of increased radio density, areas saturated by Earth-originating transmissions from satellites, deep space antennas, and long-range radars. If this object is engineered or responsive, this moment might matter. In fact, several scientists have proposed monitoring it for echoes or modulated reflections during this phase, a passive way to test if the object is absorbing or even reacting to human-made signals. There's also the question of magnetospheric interaction. Earth's orbital shell isn't empty. It's threaded with the outermost edges of the magnetosphere, and as Atlas draws closer, it may begin to interact with plasma flows related to Earth's magnetic field. That could manifest in new tail shapes, sudden discharges, or electromagnetic pulses detectable by spacecraft like ACE, WIND, or DS-COVAR. It may also be the key to revealing what kind of materials or shielding this object possesses. Meanwhile, optical tracking will intensify. Dozens of observatories, from Mount Wilson in California to La Silla in Chile, have now reprioritized their December observation schedules to focus on Atlas. The hope is that as the object comes closer, better spectral resolution and angular detail will become available. If there's structure, seams, or reflective features, now is when they'll show. But only if the object allows it. Because here's the unsettling part. The closer Atlas gets, the quieter it seems. Its outgassing, once minimal, has now become virtually non-existent. Its plasma shell remains stable, but dim. Its trajectory shifts have grown more precise, not less. In fact, it behaves like a craft entering final approach, trimming velocity, stabilizing orientation, and holding course. And that raises the final question: why Earth's orbital shell? There are dozens of places a random interstellar object could pass through, thousands of trajectories it could take without coming near us. But Atlas is entering a corridor that, in space terms, is exceedingly narrow, only a few million kilometers wide, tilted perfectly with respect to Earth's heliocentric path. Is it coincidence? Is it gravity? Is it intent? Dr. Eleanor Rue from the CNRS summed it up with unsettling precision. If this object simply passes through the shell, we observe. If it decelerates inside it, we prepare. But if it maintains orientation toward Earth beyond that line, then we're not just studying it anymore, it's studying us, and that's the true inflection point. Because now, as 3I-ATLAS edges closer to Earth's domain, we are forced to shift our role, from observers of an anomaly to participants in whatever it's becoming. The sky's no longer quiet, and whatever happens next, it's already begun.